Okay, hi, welcome everyone. So for today's online lecture, we're going to be going over using some of the built-in list methods, processing lists, and also give an introduction to sorting, which might be useful to you in some of your future assignments. So let's start out just as a quick reminder that all lists in Python are considered objects. And so what that means is, if you remember when we worked with files, we used this open built-in function. And this open built-in function returned this new type of thing that we haven't really dealt with too much. And this type of thing is an object. And in particular, what the open function did was returned a file object, which meant that built into every file object, there is a dot readline method. So we couldn't do dot readline off of anything. Like, for example, let's say I had a string, cool string equals hello, and I try to do something like cool string dot readline. I run it. Okay, so there's no attribute named readline. That's actually a really important word here. Um, so objects have built within them data and functions. And you can think about it like a package. So we already went over this in a previous lecture, but just as a quick reminder, so this dot notation, file object dot read line, is trying to access the attribute, the part of the object, the part or the function that's built in named read line. So once we have an object, based on the definition of that object, which is somewhere in Python, we can access these built-in parts. So dot something means access the part of something. So in Python, all lists are objects. So what they have, because they're objects, they have a bunch of these dot functions, these dot built-in functions, these parts that are built into them. So let's go over a couple of them. And there are very many of them, but I want to talk about a couple important ones. And of course, you should spend some time, going through the reading to make sure you cover all the ones that I didn't cover. So first one here, let's talk about the insert function. So here I have a list of strings, and I print them out. So I print the whole list using names. And then what I use is names.insert. So this dot insert function, this built-in function, takes in two arguments. The first argument is going to be what index do you want to insert a value into in the targeted list. And then the second argument is what is the value you want to insert at that index. So if we start out with Bob, Linda, Tina, Jean, and again, we can be thinking Bob, Linda, Tina, Jean, 0, 1, 2, 3. And if we inserted Louise at index 1, what we're going to see is that Linda gets bumped out of the way. She was previously at index 1. So let's see what happens here. So if I run this the first time, we see Bob, Linda, Tina, Jean, and then we inserted the value Louise at index 1. So now we have Bob. Louise is now the value at index 1. And notice that it pushed the value that was already, previously in index 1 to the right one index. So now Linda is in index 2, etc. So if you already have a list and you want to insert an item and you want to kind of push things out of the way, keep all of the values but push everything to the right one, you can use the insert function. That's a pretty handy function there. And by the way, I want to be clear on terminology. I think I already talked about this, but we already talked about functions taking an input, producing output. We can define our own functions, all of that stuff, right? When objects have functions built into them, dot insert, they're called methods. So this is actually a method that's built into any list object. Okay, so now let's look at another one, delete. Okay, so delete Oh, I'm sorry, this is remove, not delete, remove. Remove does what you would expect it to do. So we have a list of, again, strings, dog, cat, fish, chicken, and we print that list one time, and then we remove. Now, remove does not have two parameters, does not have two arguments like insert does. It only has one argument that we have to supply, and it's not an index. It's actually what value item do you want to remove from that list. So let's see what happens if I remove cat. So something that's interesting here is it actually shrunk the number of elements in the list. So we started with 4 elements. If we did the len function, it would return 4. And we ended up with a list with 3 elements in it. And everything got just kind of moved to the left. Fish and chicken, fish went to index 1, chicken went to index 2, and now we have 1 less elements. So what happens, you might think, what happens if we try, I've got an aardvark. So we want to remove the value in the list, or the element of the list that has the value aardvark, and we get an error. So list remove X is not in list. So something good to know. We can't, that there are, it makes logical sense, right? We can't remove an element with a value if none of the elements in the list have that value. Okay, so an important one. But I really want you to take note. What's another way we could do this? We could do something like this. We could say we want to remove cat. We could say pets bracket 01 is now set to an empty string. So, depending on what you're trying to do, there's no longer something useful or interpretable as a pet in index 1. But we preserve the number of elements in that list. So if that's what you need to do, you can do something like that. If you want to totally remove the element so that your list is actually shrunk, you use the remove function. So something to think about, how we can have, we can change a list by changing the value, but not reducing the number of elements. Or we could change a list by actually adding new elements or removing elements completely so that the list size changes. Okay, the next one, and this is cheater mode. For your homework, you're going to need to define linear search, something very, very similar to this, but there is a built-in method to do this. You can't use this on the homework that I assigned you. So this index, this built-in index method, is a part of every list, and what it does is we supply the index method a value, and we say for grades. So here's my list, grades.index. Tell me the index of the value f, the element that has the value f in this list. And you'll notice, so it gave me a 0, but there's 2 f's in here. So the index function will return the index of the first time, going from lowest index to highest index, it encounters a value. Let's try like C here. So 0, 1, 2, 3, 4. Grades.index. So what's the index of the value of the element that has the value C, and we get the value 4 here. So this function is useful. It's like a search function. Tell me, remember we had the in function, which said, hey, is C in this list, true or false? This is more informative. It says, okay, if C is in this list, tell me what position it's in. This might be useful because I could say, okay, once I have that value, we could make we could write some code to say index of target equals grades.index C. And once I have the index, I can actually go back and change the original list. So I could do something like grades bracket index of target, so the one that we found, now update it. Oh, I'm going to change my grade, so now it's a capital A. Print grades. All right, so what's happening here? First, created a variable. The variable references a list of string elements, and then we use the index method to find out what's the index of the item, the element in here that has a value C. So this should return 0, 1, 2, 3, 4. So index of target gets 4. And now I can use that value to actually go back to grades and say, hey, I'm doing an assignment statement. Grades bracket 4, set it to A. So let's try it out. So now there it is, my updated value in index 4. So this is a useful function. And again, these are the kinds of things out in the wild you wouldn't think twice about using. But as we're learning, I want you to learn how to make your own index function, your own searching functions. So I'll go back to how this was before. Okay, so the next one is super important for your project, for your future work. Append. So we talked about how delete, if we have 3 elements, remove. If we have 3 elements and we do remove, the list gets shrunk, and now there's 2 elements. We could also keep the same number of elements and just change one of the values of the elements. So append is kind of similar. So with append, we're going to add an element to this list. We're not changing the value of an existing element, but we're actually going to add an element to the end of the list. So now it grows by 1. So let's say I have this usernames list. And let's start with this first. So let's say I have a list of usernames and I want to set the first element to input. So let's ask the user to give us a string, and you'll see that we get an error. So I'll say Bob, and it says list assignment index out of range. So this usernames list, there's no cubbyhole in it. There's no element that has index 0. This empty list has no items in it. So if we wanted to do an assignment statement, we would need to add a new element in here first in the 0 position. And now we've got some address in memory that we can set values to, like make that address stand for our new string or whatever. So one solution to this, and this is very useful when you're building a new list from user inputted values or something like that, is to use this append method. So we're saying for this list usernames, we're going to add on to the end. And because there's no elements in it, the end of it is basically the first element. So we're just going to say glue onto it whatever the result of this input function is. Let's do Bob. And when I print usernames after that, now I have a list with 1 element. Let's see what this looks like without the input function. So what if I did usernames dot append, and now I'm going to manually type in a string instead of getting a string from user input. So we'll say this is Janet, and usernames dot append Batboy, usernames dot append Trillium. Okay, so we started with an empty list. Then we said stick on to the end. We're going to create a new element. So now the size went from 0 elements to 1 elements, and it's going to be the string Janet. Okay, now that we have that, usernames has 1 element. Now we're going to append on the end of that list Batboy. So now we had 1 element, and we're gluing onto the end. We're adding a new element with the value Batboy, and we again do it for the 3rd time, and we're appending. So to append means to stick onto the end of it without changing the original contents. So if we print all of usernames now, so I hope you can see the issue with something like this. If I did usernames dot append, usernames bracket 1, because we have an element in index 0 already, equals batboy. Why can't we do this? Because our list has only space for one element. Like if I do something like this, so what is print? What is the length? What is the length of usernames? Think about it. If we have an empty list, we append one item on, and I find out what's the length of it, should be 1. There it is. So if I try to do an assignment statement in the position 1, there's nothing there. That first element went in the 0 slot, Janet, and we're saying, okay, hey, I want to stick on, or I want to do an assignment statement for position 1 and assign the value batboy to that element. There's no element there that can take that. So that's where append can be really handy in growing your list. You think about append is kind of like an insert, except it just glues onto the end each time. You're going to use this when you want to basically a lot of places, actually, all over the place. I shouldn't limit its use cases. Okay. So as I mentioned before, please take a look at the list of all the different built-in methods, and they're useful in different contexts. Remember, so you can reverse a list, remove, we can sort, but remember for our homework, take note of, it's very explicitly stated, highlighted in red, you cannot use, these built-in functions, built-in methods. Okay, so the next thing I want to talk about is using lists and defining functions to work with lists. And I think this is something that some of you guys, if you're comfortable with it already, you can jump ahead a little bit. But I know some of you guys kind of freeze up when we start having lists and functions. So remember the basic idea behind our functions is just like a input processing output. The same thing we've been talking about all semester. So I have some value input, and I have some function, and then after processing, I have my output. So if I did something, my function, we could think about it as like a really, really simple math function. F of x equals x minus 2. Okay. And then if I plug in, here's my x, right? X, and then whatever the result is. So if we plug in like a 7 here, so if my plugged in value is 7, it goes into the function, it does all of, we substitute 7 in for x, we get 7 minus 2, and it spits out 5. And our function, once we define it, this is really the key here, is that once we create our function, it's like a reusable tool, and I can plug in other values. I can plug in, 1, 1, 2, 5, and this is now the value of x, and our function does some processing, and it returns the value 1, 1, 2, 3. Okay, so basic idea for functions. So now what if instead of a numeric value that is our parameter, what if we had a list? And it's the same idea. So let's clear this. Actually, let's see if I can undo. Okay. And so now let's say my input now, my parameter is a list. Then our function does some stuff to it. and then at the end it spits something out. It might be a single value, like if we're adding up all the values, or it might be a new list if we're modifying the list, or it even could be the same list that has been changed in the function here. So we might do something like plug in a list, do some stuff to it, spit out a list. And so our now our x would not be a number, our x would be a list. So let's look at a really basic example of that. So don't be scared combining functions and lists. Let's look at a really basic one. Here I defined a function called do nothing. It takes in a list and it just returns, it spits out that same list. And so here I have a test list and I say, okay, hey, I want to use do nothing plugging in this list. So test list 1 is being used as the argument in this function call here. And then we return the result of it and I print the result. So if we plug in 1, 2, 3, 4, 5, we expect that the result after running it through the function will also be 1, 2, 3, 4, 5. All right, so this is in the most basic case. Like, look, instead of a numeric value here, we're plugging in a list as the argument. Let's try do nothing, and we'll try it with a different test list. So test list 2 is, 7, 8, 9, 10. And if I plug in test list 2 into this function, do nothing, and we return the result, and we print the result, well, the expectation, this do nothing function, all it does is it takes in a function, takes in a list, it just returns that same list, okay? So, but this is the idea, is we could have all of our complex loop processing stuff happen nested inside of a function definition. And what that gives us is the ability to reuse whatever processing that we came up with. So now you say, oh, give me any list, and I can go through that list and give you some result. All we're doing is kind of adding a wrapper around it so that we can reuse it in different parts of our code. So let's take a look at a function where what we're doing, we're plugging in a list, and for all elements, oh my gosh, there you go. For all elements, add 1. Okay, so this is our add 1 function. We've talked about it a million times. It's like our toy function to show basic processing. And we could extend this a lot, but I want to talk about how can we take in a list, do some processing in our function, and return a new list. In this case, actually, we start with one list, we change the original list, and we spit out the changed original list. This relates to our idea of copying lists and how it's really about where in memory does the variable, what memory address does the variable reference. But we'll talk about that later. So here's add 1, and we'll just forget about all of the test code for a second. So what are we doing here? So we define add 1 to be a function. It takes in a list as, so it has a list as a parameter, takes in a list as an argument for each index. Now what I'm doing here is I'm going through all of the possible indexes of input list. So no matter how many elements we have of input list, so we actually don't know. I'm going to put ... because we don't even need to know how many elements there are in it. What we're going to do is we're going to make a parallel list that contains the indexes 0, 1, 2, 3, dot, dot, dot. And in here, you know, we might actually have our real values. The values of our list could be strings. We'll make them strings, could be other stuff. All right, maybe Bob's in there. Bob. And Gene. All right, so our idea again, like as usual when we're processing a list, is we need a way to step through the elements in our list. And we can do that by creating another list that has all of the indexes, or we can do that by having, you know, a variable. So we'll C is our counter. We start C at 0. And then after each iteration, we do C equals C plus 1. So those are the two methods. So one of them using a while loop, we have a counter variable and we just increment our index. The other one using a for loop, we use the range function to generate another list that has the same number of elements. It starts at 0 and it goes up to whatever the last index is. All right, so in this case, I'm using the for loop version. And so we generate a list of indexes. And as we go through it, so for every index in 0, 1, 2, 3, whatever, all the way up to the end of this input list, the number of items in this input list. And we could do this to make it really clear. Start at 0, go all the way up to the last element, the last index in input list. We're going to say input list bracket index is whatever that value was plus 1. So look, we're changing the actual list that we plugged in using an assignment statement. Input list bracket 0 is input list bracket 0 plus 1. Okay. Next iteration for index in this list, index will be 1. Input list bracket 1 is input list bracket 1 plus 1. So let's test this out here. And I think it's a good idea that this is in video because I know that this is where people get caught up a little bit. I'd like for you to maybe slow down, analyze it, work through it, think about why does this work. So what's our expectation here? If I plug in test list 1, 1, 2, 3, 4, 5, and then I run test list through our add one function, the end result is that we should have a list that is 2, 3, 4, 5, 6. So, and in this case, I got some, you know, kind of random values in here. So test list is 48201, and we use the same function, plug it in, plug that list in as an argument, and we should have 59312. So this is kind of, you know, baby steps into processing lists. Again, I hope that if you understand this, I hope that you kind of skipped ahead a little bit. If you didn't understand this, chew on this, because if you don't get this, nothing else is going to make sense. Play with this. Try to make your own add one. I really want you to think about, why does this line make sense? This line right here. Okay, let's move on to copying lists. And again, I'm going to start with this doesn't work. So I'm going to start out with an example of why this doesn't work. If you read the chapter on copying lists, your intuition, and it's totally right, this would be my intuition too. If I have a list, L1, and I want to make a copy of the list, why not create a new variable, L2, let's call this new list, is L1. So you might think that, oh, what that does is it just creates a new list and all of the values are in new list. And here, I'm going to make this new list. Okay. This line, though, does not do what you might expect it to do. So if I run this, so L1 is 1, 2, 3, 4, 5, and we print L1, then I say, hey, I've got a new variable, assign it to L1, or assign L1 to it rather. And then if I do new list bracket 0, so now I'm changing new list, hopefully not L1, the new value in the index in index 0 would be 500. But watch, when I do this and I print that original list, oops, I have something. Oh, that's the first. So this is L1, and then this was L1 at the end. When I did this line right here, I set new list bracket 0 to 500, I shouldn't have been able to change my first list. So this is not copying lists. I can't just create new variable, do an assignment statement, and say, hey, this list equals that list. So what happened is basically in memory, we've stored all of these values, 1, 2, 3, 4, 5, and maybe they're at address 7. Okay, so starting at address 7, I stored the bits 1, 2, 3, 4, 5, the bit codes for 1, 2, 3, 4, 5. So L1 points to address 7. Okay, and then when I did new list equals L1, what I did is I have a totally new variable, new list, that points to the exact same memory location, which means that if I change new list, I'm also changing L1. The goal here, and maybe I should draw this out a little bit. We got time for it. So here, this is not a list, okay? This is our memory, our main memory. And you guys remember, it's got a lot of similarities to lists, right? That we have the contents of each of these cells is going to be some, bit codes. And these might stand for anything we want to store. They might stand for images, they might stand for characters, they might stand for, strings or float values or whatever. It's just general storage. We could use bits to store all that. But the idea here in our memory is that each of these cells has an associated address. And this would also be in binary, but for human readable purposes, we'll say this is address 7, address 8, address 9, address 10, address 11, 12, 13, 14, and all of these would have, something in them. Some of them might be flagged to say, hey, this is open. We can make a new variable and use this. Some of them might be flagged to say, hey, this is currently in use by our program, don't touch it. So now when we do something like this, L1 equals, and we have our 1, 2, whatever. Whenever we create a new variable, we look for an open spot in memory, and that area is now reserved. It's used up. We're storing some values, So maybe we were looking through, we saw, we'll say these are used by other things, but then this one, these are available for use. Then we say, okay, L1 equals this, starting at address 9 down, change this to the bit code for 1. Change this to the bit code for 2. Change this to the bit code for 3. So the values are stored, and the variable references this memory address. Then when I do new list equals L1, I'm not looking for new memory addresses. What I'm doing is I'm just saying, hey, new list is a new variable that also points to 9. So if I'm changing new list, I'm changing all of the same actual contents in the list. All right, so what do we have to do? We have to make sure that when we create new list, it points to a totally new, different memory address. And then once we do that, we can take the values from the first list and we can copy them into the appropriate indexes. So that's our goal here, is not just point to the same memory address, but to go find a new open memory address, distinct different memory address, and then go through that first list and copy each value into the new memory address. It's a little bit, you don't need to know this stuff, but I feel like it helps clarify why doesn't this work. If you just, memorize the fact you can't do this, that's fine with me too. But it might clarify that. Okay, so how can we do this? Well, instead of saying new list equals L1, I could do something like this. New list is a list. Okay, it's not the same list, it's a list. It's an empty list. And what if I did this? New list dot append, so we're going to grow our list, whatever that first element is in L1, L1 bracket 0. So new list is a different list, it's not L1, and then I'm growing new list by appending on the first element in L1. Now, let's see what happens now if I print L1 after this, and also print, let's say, contents of L1 is, so here's L1 here, and contents of new list is new list. Right. Okay, so after going through this, we start with a list, we print that list, 1, 2, 3, 4, 5, then we initialize a new variable, and now this new variable does not reference the same memory address. We're saying, hey, it's a list, it's not the same list, it's an empty list. And then I said, okay, I want to grow new list, add an element to it, but we're going to take the value from L1. Then when we printed L1 again, it was not changed. This is what we wanted. 1, 2, 3, 4, 5 is the same as 1, 2, 3, 4, 5. And the contents for new list, so this is our new list, we copied that first value. You can make a function to do something like this. That's a very handy function to have. If we want to copy two lists, store the results of one without affecting the first one. I'm actually not going to go through this in the interest of time, but think about, we would have something like this, or maybe the signature would be, we'll say signature would be int input list, and we would have a int copied list. So a list of integers as input and a list of integers as return value. So we could also define a function that instead of updating the list that we plugged in, that it created a brand new list where every element was +1. So you remember our add one function that we defined before, we took in input list and we actually changed input list. We could adjust this just a little bit to do something like this. Temp list is a brand new list you've never seen before. For every item in input list, fill up temp list, and at the end, don't return input list, return temp list. Okay. So again, if I went a little fast, you can go back and watch it again. But the idea is, there's a distinction here between, taking in a list, changing that list, versus taking in a list, creating a brand new list that's separate, using the original list as source material to populate your new list, and returning that new list. Okay, let's see here. Okay, So now we're kind of caught up to where I wanted to be. We already talked about count twos. We already talked about count target. And now I want to walk through each of these problems, so you have like a living example of how to do them. You can go back and work through it to understand it. So in each of these problems here, again, the idea is that we're processing lists. The strategy is the same. Determine what do we want to do for a single element. Use a loop to cycle through all elements of our list. Stop the loop when we've processed all the elements or when we've reached whatever our goal is. And again, think about how we can have a transformation where the input is a list and we spit out a single value. Like, what's the sum of all of the values? What's the total if I add all the values up? Start with a list, single value. What's the average? Start with the list, what's the average of them? Or something like, what's the index of a matching item? Start with a list and maybe a search value, 7, something like that, and then spit out what's the index where you see the value 7. So list and a value, output is single value. Or we could take in a list, do some processing, and spit out another list. So take in ages, add 1 to all ages for a birthday, take in a list of inches, convert the whole list into a list of centimeters using the same values as source material. Finally, another example is that maybe we are not starting with a list, but we have keyboard input and we want to create a list from that. So just an example of some of the possible transitions we can make when we're doing stuff with lists. All right, so let's look at the average. And so here, I do not like these examples here. So let's say test list is, so let's do some really easy ones. So we'll say test list, we'll make it add up to 16 and it'll be 4 values. So in the end, we'll have 16 divided by 4 should give us 4. So I'll say 2 and then 4 and then 5 and then 5. Right. So if we add all of these up, it gives us 16. There's 4 elements in here. So we should expect for test list, if we get an average, 4. Okay. And we'll do another one, test list. Oh, we'll just do 1. That's fine in the interest of time. Okay. Okay. So we have a signature here. We're taking in a list of float values and we're returning a single float. So here's our function, our input processing output box. We can plug in any list as input. And then within here, we're going to do some processing. At the end, the goal is to return our average, whatever that average is. Now, thinking about, how do we calculate an average? The mean for a collection of numbers is we add all the numbers up, divide by the number of values. So we have our list. Maybe that's our first step, is find out how can I add up all of the values in this list. There are some built-in functions we can use. There's one called sum, but let's use a loop to do it. Okay, so we're going to use a loop to process this list. So again, what would we do for each item? Let's be thinking within this list. We want to go through every item in the list. What should we do for each item in the list? And the way that we can do this is have an accumulator where every time we encounter a value, add it into this accumulator that's growing. So I'm going to call this our sum, and I'm going to start it at 0. Makes sense, right? If we don't have any elements yet, our total sum is 0, right? Now, I want to step through every element in our given list, and for each element, do sum equals sum plus current element. Okay, so we can use the, we'll continue using the for loop version. So for, and we talked about a lot of different ways to do this loop. We could use for x and y. If you're comfortable with that, use that. But I'm just going to be consistent for this lecture. So I'm going to be thinking about indexes always. So for every index, and now we need to generate a list. Remember our parallel lists? So regardless of what's an input list, I want to generate a parallel list that has all of the indexes, 0, 1, 2, 3. So how can I do that? I can use the range function, always start at 0, and go up to the last element. Remember, all we know is we have input list, but we can find the last element by finding the length of input list. Sorry, the index of the last element is what I meant. Okay. So for every index in this list that we generated, 0, 1, 2, whatever, all the way up to the last item, and our goal was to continuously add into our accumulator. So sum is sum plus. So here's the tricky part. We don't want to add in index, because what we're going to be adding is not the real values themselves. We're going to be adding 0, 1, 2, 3, 4, whatever, right? So what we really want to do is take whatever the list that was plugged in, and we could just forget about test list for now, because this function will take in any input list. All we know is we have an input list. And so what we want to do is not add the index, but actually go back to our inputted list and add each element index. Okay. And so we're going to step through this for every index in this range. Sum equals sum plus whatever the inputted list bracket index. So index will be 0, then index will be 1, then index will be 2, etc. And then after that loop ends, now we have our total. We're not done yet though, right? We want an average. So we can return the sum divided by, well, we need the number of elements in our list. You should be thinking, well, we have a function for that. The number of elements in our input list is len input list. Okay, so there's our little input processing output machine. We plug in a list, we go through a loop, and for each iteration, we add onto an accumulator. And finally, at the end, once we've gone through all of those iterations for each element, we have our sum, and we can return sum divided by the number of elements. So let's test it out here. Should get 4. Let's see. If I have 4 elements, they add up to 16. What if I had 5 elements and they added up to 25? So I'm going to add 9. So with 5 elements that add up to 25, we should expect a 5. Okay. Right, and I hope by now, I don't need to keep reiterating that once we've defined average of list, we could plug in test list, we could plug in other lists. It's now a reusable tool that gives us the ability to, in one step, give me the average of this list. Wave your hand, do the dirty work for me, computer. All right, let's look at the next one. All right, so they got married. And so we want to update all the elements in a list of strings now. And so what we're going to do, if we see any values in our list that say Jessica, we're going to update that element so that it is Mrs. Jessica. And if we see any elements in the list that say Herb, then we're going to update that element so now it's Mr. Herb. All right, so this one's a little bit tricky because we're not going through every element and for all of them we're updating it. We could do something like this, something a little silly here, where so I'm going to go a little faster through this because we know we want to iterate through every element in the list in order to check to see, do we update or not? So for every index in, and we're going to go through all of the indexes of whatever the input list is, range starting at 0 and going up to length of input list for all of them. Now we could update all of them to just say Mr. That's not exactly what we want though, but it might be a good exercise to think about, to break the problem down. If we were on a single element, how could we update this element so that it says Mr. Herb? Well, we could say for index in blah blah, we're going to set the list. We're actually changing the list bracket index to, this is going to be a little bit different in terms of the order, but that's fine. I'm going to add a Mr. to the front of it, Mr., and using concatenation to glue strings together, plus whatever the current element is, input list bracket index. Okay, so let's see what happens with this. Isn't exactly what we want, but it might be a step in the right direction to just add to all the elements, Mr. this, Mr. that, Mr. this. So let's try it out. So now I'm going to, oh, and by the way, at the end of the function, forgot, we want to return our altered list, input list. Okay, so here's our test list here. We have a bunch of strings, and then we are going to plug test list into the function. It's going to run through the works and spit out a new list. For each of the elements, we should see Mr., 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 Mr. Okay, so it's a step in the right direction. Now let's think about it. If we want to get, we want this to be more specific than that. So we're still going to go through each item because we kind of have to do a little bit of a search. So we have to find out if the current item is Herb, then we're going to do this add a Mr. in front of it. So you might be thinking, this is one of our conditionally executed bits of code. Maybe we execute it, maybe we don't. So if it's true that the current item is Herb, then we update the current item. So if input list, the current item, bracket index, is the same as Herb, then we can update that element. So let's see if this worked. We have two Herbs here, so we should have both of them be Mr. Herb and then the rest of them unchanged. So for every index in our valid indexes, we're going to check if the input list bracket index is Herb. Then we update that input list bracket index. So this would be the same current value is updated to be Mr. plus whatever that value was before. Let's run it. Okay. So I'm going to leave the rest of it as an exercise to you. So we want to go through each item. If you see an Herb, update it to be Mr. Herb. If you see a Jessica, update it to be Mrs. Jessica. Let's see if you can do that. I'll maybe do ... Some more stuff here. That example is good because, we do a lot of processing numeric values, but lists can store any data type that we can work with. Sometimes we process lists of strings. Sometimes it's a list of Booleans. Okay, so here is our linear search. And this is the one I went over in our last lecture and is super duper important. And I'm going to walk through this 2 times. So there's 2 versions of it. The first one is like our in operator. Well, first of all, let's look at the signature. So we're defining a linear search. We take in an integer and a list of integers, and we return a Boolean. So if the value that we plugged in, search term, is in our list, then we return true. And if it's not, we return false. Okay. Again, if you're confident on this, you can skip ahead a little bit. If you're not confident, you can slow down here. This is basically the same as our in operator. And within your assignment, I don't want you to use the in operator, and you can't use the index function. So this is similar to both of those. Okay, so let's think about these test cases here. So my test list 1 is here. If I search for 5, there is a 5 in test list 1, so I expect true. Okay. If I search for 17 in test list 1, there's nothing in there, so I expect false. And so now we have test list 2. If we search for the value 199, we expect true. I see it's right there. And then if we search for the value 1, we expect false. Within this list, if I search for 1, we're going to get a false. So we have two parameters, and these can both change. Using, we could keep the list the same and change the search term, or we could keep the search term the same and change the list, or we could change both of them. This is getting very useful here to say, hey, is this value in here? Okay, so let's think about, we actually walked through this before, so I might do this one a little faster. What are we going to do on each item? And keeping in mind, our function should just spit out true if we find the correct value. If we find the targeted, if we are able to find search term, we don't need to do anything else. We're done, right? So what do we want to do on each item? We want to see, so if I'm on item 1, I want to see, is it search term? Is item 1 the same as search term? So for each item, check if current item is search term, or maybe I can say if current item is search term, then we're done. Just simply, we're done processing our list. Remember, that was one of the possibilities. We either go through all items of the list, or if we've achieved our goal, we just stop doing the loop. For each item in the list, if the current item is search term, we return true. That's it. Now, when is it false? And we already talked about this. So it's only false if we check each item, all of them, and we still haven't found search term. Remember, like, it could be that very last one that matches search term. So we have to check all of the items. So after the loop ends, so I'm going to out indent 1, I'm going to just return false. So the only way to get through this loop without spitting out true, stopping the function spitting out true, is to go through the entire loop. Okay. So for each item, so for index in range, again, 0, length. This is the length of our input list. Input list. Okay. For every index in there, if it's true that our current item is search term. The tricky part here is, what's our current item? We have our list, we have the index. So we have input list, and the current index is index. If input list bracket index is the same as whatever the supplied search term is, return true. And that means the function stops running. Finally, if we get through the whole list and we haven't seen a match yet, we'll say, hey, it's not in that list. Okay. Syntax error. Syntax error. Input list bracket index. Is it something here? Range? Guess I'll find out. Let's run it. Test list 1 is not defined. Is it? Oh, I have test list and test list 1. Okay. Well, let's make this test list 1. Okay. Input list is not defined. That's because it's a lowercase. All right. Okay. So our expected results. True, false, true, false. So if I plug in 5 in test list 1, we found a match. It's in index 0, 1, 2, 3. Great. It's also in this index here. But as long as we find 1, we should return true. Okay, expect false. All right, so it worked in all the conditions we wanted, but this is a very limited tool. You remember that example back here where I wanted to change my letter grade? Let's see, do I still have it? So we did something like go through, find the index of the C, maybe we should use an F, find the first index you see F and change it to A. And what that involved was an assignment statement. I needed to say grades, bracket, whatever the found index was. Found index is now A. The problem with our function is it just gives us a true false value. So we can't go back and say, oh, I know what the found index is. I searched for it. I found where that F was. All we can say is, yes, I found an F. So let's extend the last function a little bit to give us the ability to find the correct index. And let's see. Actually, why did I copy paste this? This is not the same version. Linear search. So this is a little bit more complicated. At least I got the signature correct. Linear search, we'll just call this linear search. Given a search term and a list of integers. If the search term is an element in the list, return the index it is in. If the search term is not an element in the list, return -1. All right, so that's going to be useful to us. I guess in Python, -1 does work as an index. Most programming languages, -1 is a great kind of sentinel index, or just like a, it's not possible to have an index in -1. We'll keep it for our example here. That's fine. Okay, so let's work through these examples first. It's a good exercise to come up with your test cases before you code. That way you're not adjusting your test cases to fit your broken code. So first, like without thinking, no, so I've got, blood will be spilled. Like this is what I expect. However you do it, it better work. So let's say if we plug in linear search and we plug in a 5 and we have test list 1, we should see 0, 1, 2, 3. This should give us 3. Okay. And then in this second example here, you remember 17 was not in test list 1. So we expect -1. Okay. And then plugging in 199 as our search term in test list 2, 0, 1, 2, 3. So we have a 199 in index 3. So we expect 3. Let's make this, let's put something else in here just to make it different. Maybe I'll make this 199. Let's put 199 here. We'll make this one 175. Okay, so when I plug in 199 and test list 2, we should get index 1. That's where index 1 is. And again, there is no value 1 in test list 2, so we should expect -1. All right. So this is very similar to the last one. Let's just copy paste. But we're going to make a little bit of an adjustment here. So for each element, as we go through each element in the input list, we are going to check to see if it is the same as search term. However, if we find a match, we don't spit out true. We have to spit out whatever the index that our loop was on. So remember here, our index is counting up each time. Right? 0, 1, 2, 3. Each time we have that current index. So really what we want to return is index. Whatever that index is on that iteration is the index that we found the first value that matches our search term. And instead of returning false, if we went through the whole list and we didn't find the value, just spit out -1. All right, what's my syntax error now? I guess I'll find out again. All right, but here's our expected values. If we run this, input list is not defined. Oh yeah, it's my lowercase. All right, 3, -1, 1, -1. All right, excellent. Is this problem? This was problem 5, not problem 4. Okay. Okay, so this one is important because it applies to your assignment. So these two are important and they relate directly to our sorting algorithm stuff. So like linear search, we're going to do 2 versions. One of them, 2 different, slightly different versions of the same algorithm. So in the first one, we're going to take in a list. So we want to find the maximum value, not index. So in this set of values, what's the biggest one that you see? The second version is we're going to say, hey, find me the biggest value and give me the index, the position it's in. That's going to be useful to you. Okay, so once again, we can think about, what are we going to do for one item? Repeat that action and then loop whenever we're finished. So that loop whenever we're finished, we could start thinking about it there, that if I go through this list and I'm looking for the biggest item, well, it could be that the last item is the biggest item. Again, this is a algorithm where we do have to check all of the values. So it's a little bit different than our our linear search. We're like, hey, I found one, we're done, right? We don't need to continue going on. So this one, we do need to check all of the values to see, it could be that that last one is the biggest one or something deep in the middle of it. So that's something to think about. Now, how do we do this? What are we going to do on each iteration? So I'm on item 1, and I want to find the biggest one. And you think about it as we go, the biggest one might change. So we might say, if I'm on 1, I've never seen anything else. 1 is the biggest one I've ever seen, right? And we get to the second element here, I'm at 3. So is 3 bigger than the biggest one we've ever seen so far? Yes. So that means we're going to update what the biggest one is that we've seen so far. So this algorithm, I like to call it like a king of the hill kind of situation, where we're going to keep track of what's the current king of the hill. And we can use this same kind of thinking for finding the minimum or the maximum when we're iterating through a list. So we got to go through and keep track. What's the biggest one I've seen so far? We need something to keep track of that. We can't forget it from step to step. So what this suggests to me is we need a variable. So we will need to go through all of the elements in our list. That's one thing that needs to change in our program, is, like have a list or have some index variable. We also need a variable for current maximum, or we'll say maximum max so far. Okay. I'm not sure what to put for the value before the loop. But maybe we'll just take care of that right now. If I'm on the very first element, like I said, it's the biggest one we've seen so far. We shouldn't set this to 0, by the way, because what if 0 is not an element in the list? Or we shouldn't set it to like -1000, because what if we go through this list and we find out that, we'll say biggest element is 100,000. And what if we find out that none of the elements get that high? Then our king of the hill would always be 100,000, but it wouldn't reflect the values that are actually in the list, right? So we have to use a value from this list just to initialize our king of the hill. And we might as well just say, if we're on the first element, just say it is input list, bracket 0. All right, great. So now we have something to compare it to, and we want to continue doing like a greater than sign comparison. If it's true that the current item is bigger than the king of the hill, if current item, oh, well, we got to go through all the elements of our list. So for index in range, starting at 0, going up to the length input list, okay, for all of the elements in the list, if it's true that the current item from our list, so our list is input list, if input list bracket index, the current item, is bigger than whatever our maximum is so far, max so far. So here's the part that's kind of interesting, maybe a little confusing the first time you see it. We're going to update what the max so far is. So as we go, if we find an element that's bigger than the king of the hill, that's the new king of the hill. So max so far gets updated. Max so far is now the current item, input list, bracket index. And we go through each item. 1 is the king of the hill. Is 3 bigger than 1? Yes. So now the king of the hill is 3. Is 2 bigger than 3? No, don't do anything. Is 5 bigger than the king of the hill? Yes, the new king of the hill is 5. Is 2 bigger than 5? So you notice that max so far, it only goes up. It never goes down. Only when we encounter a value, that is bigger than the current king of the hill do we update the king of the hill. All right, and finally, in the last, this whole function is meant to spit out the biggest value we've seen. If we get to the end, well, the max so far is the king of the hill. So we're just going to return max so far. All right. So in this first one here, in this function, we expect that 10 will be the king of the hill. Expect 10. That's the maximum value. And in the second one here, what's the biggest value? Is 200. And let's test it out. Test list 1 is not defined. Okay. So it looks like a lot, but if you just think about what the actions are, it's really not that much. We're going through each item in the list. We're updating our king of the hill if the current item is bigger. That's it. And at the end, we know the value, not the index, the value of the king of the hill. All right, so we're getting near the end here. Finding the index of the smallest value. You can use the same king of the hill approach. You wouldn't be using a greater than sign, right? But we don't want to return the maximum value. We want to return the index. So you might, instead of maintaining the maximum value so far, when you see a value that's bigger than the maximum, update the index of the maximum value. So keep track of what's the index of the biggest value, and at the end you can return the index. Okay, so for populating a list using user inputted integers, you're going to use a loop. In each iteration, you're going to do the little trick we used with append. Use input, append that value onto the list. That's it. So I'll let you do that one on your own. So we're in the kind of like the last couple minutes here. Just in case you were working on the extra credit, I wanted to spend maybe 10 minutes talking about sorting algorithms. And this stuff, if it's beyond what you're working on right now, don't worry about it. But it's very, very interesting. Again, this is a very practical problem. I have a bunch of pieces of information, and I want to put them in order from lowest to highest or highest to lowest. Think about your Amazon searches or Google searches or anything like that. We have a lot of pieces of information. We want to put them in order because they're going to be more useful to us for whatever reason. Now, the first thing I always say when you're dealing with sorting algorithms, and in fact, when we're doing list processing too, but especially with sorting algorithms, is to get into a mindset where the values in your list are tangible physical things, okay? So just imagine, here's our list, and you've got a bunch of items in our list. And really like this, I really want to step away from abstract, complicated code stuff for a second. Just think, okay, hey, you've got a list of elements. You've got a bunch of blocks. Okay, they have numeric values. We'll say 7, 2, 1, 3. Okay. So we got some blocks in front of us, and what would be your strategy if you're explaining it to someone else? Maybe you're explaining it to your, little cousin or something like that. How could you put these in order? So I was talking during office hours to a couple students, and they had different approaches that were equally valid. And it really starts with something as basic as, in one case, one of the students said, okay, well, what I would do is at first I'd look for the smallest one. Okay, there's one. And I would take the smallest one and I would move it to the beginning. And then I have these remaining items. And again, I would find the smallest one and then move it to that second position. So over and over and over in a loop, we're going to go find the smallest one and move it to the beginning. But notice it is bumped up one each time. So in the second time we do this, so if we found one, we put it at the very beginning. When we find two, we actually don't put two at the beginning of the output. We put two in the next position. Okay. This strategy is the beginnings of an algorithm called selection sort, and it's one of the easiest ones to grasp. Okay, so in selection sort, we're going to have a list, and what we want to do in this case, we're going to shuffle the items in the same list. Okay, so we're not going to have two different lists. We have one list, and so we need to keep track of our indexes. Now, actually, the first step of selection sort is our find min algorithm. Go through all of the elements in the list, tell me the index of the smallest, actually, I should circle this. Tell me the index of the smallest element in the list. And once you've found that, we're going to swap. Okay, we're going to change the positions. This goes over here, and this one goes over here. Okay. So we had 7 and 1, right? So this would be 1, this would be 7. So if you think about, processing this processing this list, we would need one loop to use our find minimum function or find minimum algorithm to go through all of the elements in the list, find the smallest one. But our list is not yet sorted. So this is in the right position, this is in the right position, but then we have 7 and 3. These are still not in the right positions. So what this suggests is, for this particular algorithm, we need to do multiple loops of loops. So this is a nested loop. So basically, we go through each targeted index that we want to find the smallest for. So we start at index 0, find the smallest, swap with index 0. The next outer loop that we do is we start at index 1, go through all of the remaining items, because that's in its right spot. So go through all the remaining items, it's another loop, and then swap. Okay, so think about how we couldn't do that with just a single loop. We would need a loop. The outer loop is going to be counting off the targeted swap spots. This is like the sorted, 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 and we're done. The inner loop is going through the remaining items and finding the smallest item. Okay, so that's one algorithm that totally works. Let's think of another one. Actually, let's see. Do I get these? Okay, great. All right, almost done here. Another algorithm another student came up with independently was to say, hey, what if I'm not looking at the big picture, but what if I just go and do comparisons of the elements right next to each other? Is 7 in its right spot compared to 2? Or is index I smaller than index I plus 1? Is it true? The element in index I. If it's true, then the swap happens, but it's not like over here and over here. It's just like a little tiny mini swap right here. So this would be 2, 2, and then 7. Okay, once that's done, then we compare the next two of them. Is 7 in its right spot? You know, we got 2 and 7 here. No, it's not. All right, so then we do another mini swap here. And we're definitely in, you know, like office hours mode. If you're done with this, I imagine you probably, you know, I don't need to tell you that that you can go. But if you're curious, I'll continue with this. So we see that these two are out of position. So let's do 7 and 1. So this would now be 1 and 7. All right, so we compared these two indexes, compared these two indexes, and we compare these two indexes. And again, 7 is bigger than 3. If we're going in ascending order, then 7 and 3 goes to 3 and 7. All right, so that was one pass through all the indexes. That's one loop. But notice that our values are still not in order. But if you can use a little imagination, you can see that if we continued going through and doing this procedure, compare to, compare to, compare to, and swap, 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 and we kept doing this, eventually the biggest values would bubble up to the top and the smallest values would be left behind in the correct order. So two things that this suggests. So one of them is, again, we have a loop of loops. We have a loop on the outside and a loop on the inside. The loop on the inside is going through all of the indexes and swapping. The loop on the outside is saying, hey, if I saw that there was any changes, maybe we need to do another iteration. The only time that you can say the outer loop is done is if you go through an inner loop and you say, oh, I didn't see any changes. That means you're done. That means you're in order and your sorting is done. Okay, so as I mentioned, there's a lot of different approaches to this. And this is one of my favorite videos of all time with regards to computer science. We'll say sorting algorithms visualized.
Learn to code online in less than a year. Discover the CSULB Software Development Bootcamp.
All right, so the idea here is that we have a list of unsorted values. Just imagine the height of the value is the numeric quantity. We'll just pretend for now these are all positive integers or something like that. So maybe this is a 20, then this is like a 13, and then this is like a 14, and then this is like a 3. So our values, our goal is to get them from lowest to highest, organized from lowest to highest. And what's interesting here is that we have multiple different algorithms we can use to accomplish the same goal. Plug in an unsorted list and give me in the end a sorted list. So here's bubble sort, here's merge sort, here's selection sort, shell sort, insertion sort, quick sort. And you can also see this opens up some interesting conversation about how there are different tools for the same job and some of them might be better than others. So let's watch these. So they're all given the same unsorted list, and let's allow them to work through the algorithm. Let's see which one gets the list in order fastest. Quick sort, merge sort. There's selection sort up there. There's bubble sort. So let me pause this for a second, and I want to point out this guy and this guy. Or maybe they're gals, I don't know. Here's selection sort, the algorithm we were just talking about, where we go through all of the items, find the smallest one, stick it at the beginning, or do a swap. In fact, let me slow this down, make it real slow, and just watch what's happening up here on selection sort. So we already have at the beginning, let's say we have a lot of unsorted elements, and we're going to go through and find the smallest one and then swap it to the beginning. Okay, there's the smallest one. We go through, what's the king of the hill? King of the hill. Okay, swap with that one. All right, what's the king of the hill? What's the smallest one we've seen so far? Okay, swap it to the beginning. So here's selection sort. And if you look down here, here's our bubble sort. We're going through each element, and if each pair, if they're out of order, swap them. And you can see this green part here is the large value that is bubbled up to the top. You see the little swaps that are happening on the fly there. All right, so we don't have time, unfortunately, to go into it. It's the topic of your future classes if you take any CS classes, any future CS classes. But this idea that we have different algorithms we can use, and again, these are algorithms, so you can implement them in different programming languages. They're just different strategies, like abstract strategies for solving the same problem. And so not only do we have different results, but also in different scenarios, some of them perform better than others. Like we think about how many steps did it take, how many swaps did you have to do, or maybe how many comparisons did you have to do. So in this scenario, we still have a bunch of unsorted values, but the difference is that there's a lot of repeats. So instead of having values that are like all over the place, we have a lot of 17s and a lot of 5s, and a lot of 20s. So you can see in this situation, some of the algorithms have been performed some perform better. Let's see, that's another scenario. Another scenario is what if we start with a reversed list? And imagine, we don't know what's in our list. A lot of the time when we're doing this, we don't know what the order is, what we want. We have an idea of what we want in the end. So we may have a situation where the list is already in reverse order. Some of the algorithms perform better than others. So bringing it back to the work that you're going to do. So you're not going to get much out of a visualization like this. It's kind of a neat little toy for you to visualize what's happening. But go and research these algorithms and look at how are these implemented. They're all kind of classic computer science algorithms that they're known and documented many places. And I would suggest, if you're really, really unsure which one to do, is start with selection sort. It's very clear to me. Find the smallest, put it at the beginning. Find the smallest, put it at the beginning. Look at cocktail sort, by the way, is a variation of our selection sort, actually. Cocktail sort, let's see. It's funny. So we go through the remaining items, we find the biggest one, stick it on the right side. Then we go through, we find the smallest one, and we do a swap it into the beginning. What's the biggest one that we've seen out of the remaining unsorted ones? Stick it on the right. Find the smallest one. That makes sense. There's a logic to it. All right, we went way over. So that's it for today's lecture. I'll see you at our next lecture, and feel free to come in, chat with me during office hours, or send me emails if you have any questions. And have a lovely day or evening.